Okay, so good morning to all. We are discussing the unit number 4, operating system, that is nothing but the memory management technique. So up till now we have discussed about the how the memory management is done with the help of memory management unit, that is MMU, right? So MMU stands for your memory management unit, and this memory management unit consists of your relocation register and the base register, right? So any instruction or any process need to be executed, that must be placed inside the main memory for its execution, right? So what we have to do here? So CPU generates the logical address, or one can say that the virtual addresses for the execution of that particular instruction, and this virtual address or whatever may be the logical address which is generated by the CPU, that is to be converted into the physical address. Logical address is to be converted into the physical address or actual address for the execution. So this particular task is carried out by your MMU, that is memory management unit, right? So so that each instruction or each process, though the CPU generates some logical address, but its physical address is given by your MMU, and that is nothing but the actual address. For example, if his logical address is 300, right? But the memory management unit gives you some value in addition to base register and limit register. It gives you 1000 is the memory address. So then the that particular process or that particular instruction is being loaded at the 1000 memory location, and it starts its execution from 1000th that 1000th memory location, right? So this is the way. And after that we have also seen the concept of the what we can say the dynamic loading and dynamic linking. Means we are not going to load the until and unless that module is required. In case of dynamic loading and in case of dynamic linking, the linking is postponed till the execution time. So the header files or the whatever be the library files, they are not being linked, or as and when they are required, they are being linked at the execution time, and then and after that the execution will start. And also we have seen the concept of swapping, means the placing the processes to and fro, means from secondary storage to the RAM memory, and from RAM memory to the secondary storage. Swap in, swap out. You are putting inside the main memory, it is called as a swap in, and you are removing the process from the main memory, it is called as the swap out. Now, the most important concept that we are going to discuss is nothing but contiguous allocation. Contiguous allocation of the memory, and contiguous allocation has two part, that is nothing but the single partition allocation and multiple partition allocation, that we are going to discuss today. And along with this means MMU, that is nothing but memory management unit gives us the location where that particular process is to be loaded inside the main memory. So what happen? Single partition allocation means what? What happen if the memory is considered, say for example we have 1 GB, 1 GB or 1000 MB of memory is available, and if the 1000 memory it is considered as a single block of array, that is called as a single partition allocation. If this is the scenario, then what is going to happen? How the processes are loaded in the memory and how they are being executed, right? And if suppose if we partition the memory some into some small partition, then how the memory allocation takes place, that also we have to see here. So let us start with the single partition allocation. The if operating system resides in low memory and user process in the high memory, so you know that suppose if we assume, so this is our consider this as your main memory, it is a 1 GB of memory. Say for example I can write here, it is the 1000 MB of memory is available, and initial part, for example the initial 200 0 to 200 block of the memory, it is allocated to operating system. So this particular block you are going to consider as a single partition only. Getting my point out? In single partition allocation, we are considering the entire memory as a single block of array or single block where the processes can be stored in the available area, right? So, for example, if also need to protect user process from another process, and this protection is achieved with the help of relocation register and the limit register. Already we have discussed that the with the help of location register, with the help of relocation register and the relocation register and the limit register, what we are doing here, we are achieving the protection in the system, means that user processes must be kept separated from the system processes, or system processes In other words, we can say that system process must be protected, must be kept separated from the user processes, right? So each logical address must be less than that of limit register address. When CPU scheduler selects a process for execution, a dispatcher or CPU scheduler needs relocation and limit register, means whatever may be the value of its relocation register, or the whatever may be the value of its base register, and the value of limit register, that must be known in advance. That is the value of limit register and the value of base register. If this value you known in advance, then actual physical address we are going to calculate, or we are going to get here. Meaning is that logical address generated by the CPU, say for example 300 is the logical address. Any address it can generate because it is CPU. And how the logical addresses are given? So logical addresses are given or calculated, or it is given by your CPU. Means if it is a 8-bit processor, you can have logical address between 2 raised to 8 address space. Logical address space is 2 raised to 8, means 256 total number of addresses are available. If it is a 16-bit processor, 2 raised to 16, meaning is that 026556. These are total number of addresses are available. So within that particular address space, CPU may generate one address. CPU may generate one address, right? So in that case, what is happening? So in this particular case, suppose the address is being generated. Suppose a logical address is being generated, say for example 300. This 300 address, it is now calculated with the help of this 300 and with the help of this limit register and the relocation register. The physical address is being calculated. The physical address is being calculated, right? So once the physical address is calculated, means actually we will get here. Actually, we will get actual address or the exact address for that particular instruction to be executed, right? So single partition allocation, in simple word, we can define that in case of single partition allocation, what we are doing here, we are considering the operating, we are considering this RAM memory as a huge, only a single partition. This partition is considered as a single partition, and with the help of the values, with the help of the value of the limit register and the relocation register, the actual address is calculated. So whatever may be the actual, so address may be, say for example 1000. Say for example actual address is calculated as a 1000. So here 1000 memory, say for example 1000 is here. So the that particular instruction is loaded into this 1000 memory location, right? Or say for example actual address is calculated as a 500 or 501, say for example. So this is nothing but your 501th block, and here that instruction or process P1 is loaded, and it starts its execution from here itself. Getting my point? So this is the way how in case of single partition allocation, the memory is considered as a single block of array, or only a single partition, where operating system code is placed in the lower address space, that is from example 0 to 100 or 200, whatever it may be, and rest of the part, this 200 to 1000, it is assigned, or it is this will be kept for the user processes. This will be kept for the user process, right? The next part is nothing but your multiple partition allocation. Multiple partition allocation. But just give me 1 minute. I have one important call here. Okay, so coming back to our multiple partition allocation, here we can say that how to allocate memory to various processes. Now this thing is possible if there are limited number of processes. This thing one can say that it is possible if there are limited number of processes, but there are n number of processes. Say for example P1 dot dot up to Pn. These are the n number of processes are available in the system. Then how? So this single partition allocation may not be effective or it may not be useful if there are n number of processes, right? Because MMU is not able to generate all the physical addresses for the processes P1 to Pn. So in that case, the simple way is achieved here, and that is called as the multiple partition allocation. So in case of multiple partition allocation, it divides memory into number of small fixed size partition. It divides the memory into number of small fixed size partition. So each partition may contain exactly one process. So just 1 minute. Okay, so in case of multiple partition allocation, in case of multiple, say again, consider the RAM memory. So initial part allocated to operating system, and now this particular user block, or one can say that this is the reserve block for the one can say users. It is now reserved, or it is partitioned into multiple partition. It is partitioned into multiple number of partition, and here each process contain in exactly in one partition. Exactly one partition contains the exactly one process. Say for example, P1 is loaded in this partition. This is partition number 1. This is partition number 2. This is partition number 3. Partition number 4. Partition number 5. So like this way, like this, and the partition may have different sizes. And the size of the partition, it is depend upon the size, whatever may be the amount of memory required by that particular process, right? So meaning is that, so say for example, process number P1 required 100 MB of memory. Process number P1 required 100 MB of memory. So this particular partition is becoming of 100 MB of size. Process number P2. Process number P2 require 150 MB of memory. So this partition number, whatever it may be, it may be of size of 150. Process number P5, for example, process number P5, it requires, say for example, 350 MB of memory. So this much amount of memory, this much partition, correct, but this much partition, 350 MB size partition is created, and this is allocated to the process number P5, right? So the general scenario of this particular multiple partition allocation is that, so here the initial part is assigned to operating system, and the rest of the this partition, rest of the user part, it is divided into the multiple number of partition as per the requirement of the process, So meaning is that each partition may contain exactly one process. That is the degree of multiprogramming bound to number of partition. Degree of multiprogramming bound to number of partition. If I say that if there are 10 number of processes in the system, if I say, for example, there are 10 number of processes, so meaning is that there are 10 different partition that accommodates 10 different processes. Getting my point or not? If I say that there are 10 number of processes in the system, so that means that there are 10 different partitions. That means that 10 different partitions, and these 10 partitions are created, and each partition contain exactly one process, and these 10 processes are being executed simultaneously or concurrently, right? So when partition is free, when the partition becomes free, the process is selected from the input queue and loaded inside the free space. Say for example, P2 process completely execute. P2 process completely execute. So after complete execution, it will be removed from the main memory, and this 150 amount of memory block is now getting free. 150 amount of memory block is getting free, and here this free memory space, or this particular free memory area, it is now being available to the new process. So newly arrived process may be placed inside this particular memory block. So when the process terminates, so exactly the partition becomes available and used by the batch operating system. So operating system keeps table indicating which part of the memory are currently available and which part is currently occupied. Which part of the memory is currently available and which part of the memory is currently occupied here. So this is the thing here. So operating system has to mention that how many partitions are there and which partition contains which process, and once the process is being terminated, so which part are being currently available, so that the next process must be placed inside that particular partition, right? So initially all memory is available for user process and considered as a large block, and that is called as the whole. So you can remember this concept, that is whole means initially say for example 0 to 4, see this figure here, 0 to 400K, this memory block is allocated to operating system, and 2560K means 2560K kilobyte of main memory is available. So out of that 400K is given to operating system processes, and for this 2160 minus 400, that is nothing but 2160 part is only remaining for the user process. So this is called as the whole. This particular memory block is called as the whole, where your all other processes they can occupy and they can execute it within that particular user area. So when process arrives and need memory, we search for a hole large enough for this particular process. So initially the whole size one can say it is nothing but 2156K. And if we find, we allocate only as much as memory it is needed. And if we find that particular hole which is big enough, then we can allocate the memory. We can allocate the memory for that particular process. Process is being executed, and after execution, it will be removed from that particular memory, and again new hole is created. So we'll consider this one example. So from the example, the concept will become more clear to you. So assume that 2560K memory is available and resident operating system requires 400K of memory, okay, as given in this particular figure. And there are 5 different processes they arrived in the system, and their memory demands are given here. Process number P1, it requires 600 kilobyte of memory and the execution time is 10 milliseconds. The process number P2, it requires 1000 kilobyte of memory and the execution time is 5 milliseconds. The process number P3 requires 300 kilobyte of memory and the execution time required is 20. Process P4 having memory size 700K and the time is equal to 8 milliseconds. This is the execution time. This column indicates the execution time. This column indicates the memory required for the complete execution of that particular process, and these are the 5 different processes available in the system. So if we select FCFS policy, scheduling is there, we can immediately allocate the memory to process P1, P2, and P3. Now assume that we have this much amount of memory is available, means 2160 K is the space available, and there is a demand for 600K, 1000K, 300K, 700K, and 500K. Demands are given by the process for their execution. So initially, the P1 is taken for the execution and it requires 600K. So 400 plus 600. So this requires total how much amount of memory? 600K of memory. So 400 plus 600 means 1000K. So up to 1000K block, it is now being allocated to the process P1. From 1000 to 2000 means P2 requires 1000K of memory. So here 1000K memory is given to P2 process. The next is 300K is required for P3 process, means from 2000 to 2030 means this 300K is memory is given to the process P3. And now see how much amount of, or what is the size of hole. Now this is the whole size, and whole size is nothing but here 2560 minus 2300, that comes out to be 260, correct? It is nothing but the 260. This is nothing but the size of hole. This is nothing but the size of hole. Hole is nothing but the free memory, or the memory which is free available in the main memory. Though this is not occupied. This is not occupied. This portion is free, and this is called as a hole, and the size is 260 KB is available. But this 260 KB, now remember this point, this 260 KB though memory is available, but we cannot allocate this 260 KB to the P4 process as well as the P5 process, because P4 process requires 700K and P5 process requires 500K of memory. So neither of the process can be satisfied with this 260K. Hence that remains as it is. That whole remains. So we can say that this is the A picture, and A figure gives us the P1 is in execution state, P2 is in execution state, P3 is in execution state. At the same time, P4 and P5, they are in a waiting state. They are in a waiting state, and we can say that the whole size is 260 kilobyte is available, means 260 kilobyte memory is free. Now next part, or one can say the next step. Now P2 terminate. Because why the P2 terminate? Because the execution time for P2 process is only 5 milliseconds. So after 5 milliseconds, if we check the scenario in the main memory, after 5 milliseconds, if we check the scenario in the main memory, we will find that P2 process executes successfully or completely, and as it executes completely, the P2 is removed from the main memory. So see this figure number B. So P1 is as it is because it requires 10 milliseconds. P2 terminate here, P2 process terminates, and as soon as P2 terminate, this 1000K block is now becoming free. P3 is as it is because P3 currently in a running state. It execution time is 20 milliseconds here, and this initial hole, that is hole number 1, is as it is. This is 260K hole and this is 1000K hole. Two holes are now available in the main memory, right? Now after some time, see here what we have to do here. So you come to our operating system, come to know that yes, there is a 1000K space is now becoming free. So it will immediately take P4 process. Next process is P4. It will immediately go for the P4 process, and P4 is taken for the execution. So here we have written here P4 is allocated memory. So P4 is placed here from 1000 to, and P4 require how much memory? 700K. So 1000 plus 700 means 1700. So P4 occupies the memory space in this particular thing, and here 1700 to 2000, this much hole is being created, and the hole size is 300K. Here is hole is created 300K, and initial 260K hole is as it is. So at the scenario of the main memory is like this. The P1 is in a running state, P1 is currently in an execution state, P4 is currently in execution state, and P3 is currently in execution state. And the free memory size is available in two holes. One hole is of size 300K and second hole is of size 260K. Getting this point? Now again, after some time, after 10 milliseconds, P1 process terminates, because here now the 10 milliseconds completes. So P1 process terminates after 10 milliseconds of execution time. So after removing that P1 process, now it creates the whole of 600K here. It creates the whole of 600K. And P4 is as it is, currently running state. This whole of size 300K is as it is. P3 is in a running state, and the whole of size 360K is as it is in the process. Now here operating system come to know that yes, the process is removed from the memory and there may be some space which is freely available. So P5 process, next process P5, which require only 500K of memory, it is taken and it is placed here. So 400 plus 500, that becomes your 900. And still now here it creates the third hole of size 100. It creates the third hole of the size 100. This hole is of size 300 and this hole is of size 260K. So there are three different hole number 1, hole number 2, and hole number 3. And the process P5 is in a running state, process P4 is in a running state, and process P3 is in a running state. Okay. Now the point of discussion, or the point is to be noticed, is that so there are 5 processes in the system. They get the chance to execute and they get memory one after another, right? And they create how many holes? The 3 holes are being created here. 3 holes are being created. And suppose the next new process arrived in the system, that is a P6 process. Next process arrived in the system, that is P6 process, and it requires, say for example, 400 KB of memory. Its memory requirement is, say for example, only 400K. So we cannot allocate the P3 process inside the main memory. Why? Though the total memory, so 100, if you can calculate 100 plus this particular 300 plus 260, so the total free space available is equal to 400 plus 660. That is nothing but your 660K memory is available. The memory is available, right? 660K total memory is available, but this 660K memory, it is not in a contiguous format. The memory, so important point is to be remember, though addition of the free space is much more, 660 is much more than 400K. So theoretically we can say that the free space is more as compared to the demand of the new process, but still we cannot allocate the process in the main memory. Why? Because though this space is available, though the holes are available, but these holes are scattered in the main memory. You cannot combine these holes, remember this point. Because why? Because you are giving this thing, you are giving their addresses. 400 is the base address for the P5 process, and its limit address is, say for example, 500. The 1000 is the base address for the P4 process, and its limit address is 700. So 1700. So limit is 700. So base address and the limit address is given for each process. You cannot combine all holes together, and you cannot shift all the processes to one side and holes to one side. This is not possible, right? So meaning is that the holes are created of the smaller size. The holes are created of the smaller size in the main memory. So these holes are nothing but your wastage of memory. These holes are nothing but simply wastage of memory, because this particular memory, it is not utilized. You cannot use this amount of memory for the allocation of any process. For the allocation of any process. That's why we can say that the memory is not utilized properly with the help of this particular allocation scheme, multiple partition allocation, and these holes are scattered. The holes are scattered inside the main memory, and this particular phenomenon is called as the external fragmentation of the memory. So we can say that memory is fragmented. So main memory, though it is available, but it is not in a contiguous format. It is fragmented. It is in the form of fragments. There are different fragments of the memory, and they are scattered inside the main memory. Though together their size is very big, but it is not in a contiguous, or it is not in a one can say it is not in a single format. They are scattered inside the main memory. That is nothing but the wastage, and this particular phenomenon is called as the external fragmentation of the memory. It is called as the external memory fragmentation. Means though memory is available, but it is not useful for any of the process. Though memory is available, but it is not useful because it is scattered in the form of small holes or small partition inside the main memory. Hence, together though their sum is very big, but as they are not in a contiguous format, they cannot be allocated to of the process, any of the process, and this process has to wait here because till it gets 400K of memory in a single contiguous format, right? So this is the way, and this is called as the external fragmentation of the memory. This particular phenomenon is called as the external fragmentation. Memory is fragmented. Getting this point? Okay. So we'll just go to the next slide. We are discussing this multiple partition allocation. So just read it. In general, there is at any time a set of holes of various sizes scattered through the memory. Already we have discussed this. When process arrives and need memory, it search set of hole that is large enough for this. For example, it requires 400K. So it will search for the hole or the free space that is equal to 400K. If the hole is too large, then it is split into two. So if the hole available is 600K and your memory require 400K, so what it does here, it takes only 400K and it will give, or it will leave 200K as nothing but the whole, or 200K KB of memory remains as a whole. So one part is allocated to the process and one part returned to the set of holes, means the another hole is being created. Already we have seen this. So if the new hole adjacent to other hole, so the holes are merged to form a large hole. If they are adjacent, they are near to each other, they are going to form the new hole. But if they are not adjacent, they are far from each other, they are not going to combine, they are not going to merge. At this point, it check whether new process waiting for the memory. So if so, it can assign new hole to them. So this procedure is called dynamic storage allocation problem. That is how to satisfy requests for the size n from a list of free holes, right? The solution of for this particular problem is given by first fit, best fit, and worst fit memory strategy. So we have to discuss about the algorithm, that is nothing but the first fit algorithm, best fit algorithm, and worst fit algorithm. Algorithm in the sense how the demand of that particular process is being fulfilled. So first fit means what? Allocate the first hole that is big enough. So process arrived, say for example 400K is its demand. P1 arrived and its memory demand is, say for example 400K. And what we are going to see, we are searching, we in the operating system search in the memory and say for example any hole which is available, which is big enough to accommodate this 400K, immediately allocate that particular hole to that particular to that particular process. So whole size is available, say for example 500K. So immediately that 500K is given to 400K of process, and it will allocate 400K to the process, and 100K becomes the it remains as it is as a free space, or as in the form of hole, right? So that is called as the first fit strategy. That is, search can start at the beginning of the set of holes and stop the search as soon as we find the free hole big enough. As soon as we find the free hole that is big enough, right? The second algorithm is nothing but your best fit strategy. So best fit strategy, what it says, allocate the smallest hole that is big enough. Allocate the smallest hole that is big enough means to that produces the smallest leftover hole. Demand is 400K. So you have, and there are two holes are available. Suppose one hole is of the size 500 and another hole is of the size 410, for example. So which hole is the best suitable for this particular 400K of memory? This second hole is best suitable because it is having 410 spaces available. So out of 410, 400 MB is 400 KB is allocated to that particular P1 process, and only 10 MB space will be remains as a empty space or as a whole space, right? So residue, one can say smallest leftover, it will give you the smallest leftover. Leftover means smallest amount of hole size. That is called as the best fit strategy. And in case of worst fit strategy, allocate the largest possible hole. Means for again the second in suppose the same example, if the 400K process is allocated to the hole of size 500K, so meaning is that you are creating the hole of size 100K, right? So by following this worst fit strategy, you are creating the hole of larger size, and as the whole of larger sizes as the whole of larger size are created, they are scattered inside the main memory, and they cannot be further utilized by any of the process, right? Means what you are doing here, you are unnecessarily you are creating the holes in the system that memory is not utilized for the for any process, right? So serves the entire list and produces the largest leftover hole. So see, this thing is important. First fit, allocate the first hole that is big enough to that particular process. Best fit, allocate the smallest hole that is big enough to that particular process. So here you have to search the entire list, and after searching the list, that particular hole must create the smallest leftover. And worst fit strategy tells that allocate the largest possible hole to that particular process, meaning is that serve the entire list, and that produces the largest leftover hole. That produces the largest leftover hole. So first fit and best fit are the better than the worst fit in the time and storage utilization. So if you want the proper memory utilization, if you want proper memory allocation to all the process, we must go for the best fit strategy or the first fit strategy. If we go for the worst fit strategy, it will unnecessarily create the holes in the memory, and that holes are not utilized by any of the process, right? The next is external and internal fragmentation. Internal and external fragmentation. So this particular above algorithm means the algorithm which we are discussing now, they are suffering from the external fragmentation. So external fragmentation means what already we have discussed. So as the processes are loaded and removed from the memory, the free memory space broken into little pieces. The free memory space is broken into little pieces. Just now we have seen in the example. So external fragmentation exists when enough total memory space exists, but not in a contiguous. So remember this point. Enough total memory spaces exist, but not in a contiguous format. That is called as the external fragmentation of the memory. Storage fragmented into larger amount of the small holes. For example, in figure A, external fragmentation is 260K in figure A. The external fragmentation means it is the whole of size 260K is available. The it is too small to satisfy request of the process. In figure C, the total external fragmentation size is 260K. If that is nothing but one hole is of size 300K and another hole is of size 260K. So total is 560K. But the demand of the next process, but the demand of the process is 500K. But still you cannot allocate the 500K process to this 560K because this 560K, it is not in a contiguous format, or they are, it is not in a single format, right? So this memory is large enough to satisfy the request of P5 process, because P5 require only 500K of memory. This free memory is not contiguous. Free space is fragmented into number of pieces that cannot satisfy request of any process. That cannot satisfy the request of the any process. So this fragmentation problem can become severe. So another problem for multiple partition allocation, this is nothing but the another problem. This is called as the external fragmentation. This particular part is called as the external memory fragmentation, right? So external, so once again see this figure. So from this figure it will be more clear to you. So this fragment is of size 100. This fragment, memory fragment, is of size 300, and this is of size 260K. So totally 660K is memory available, but they cannot fulfill the request of even 400K of memory, because though the memory is available, but it is not in a contiguous format. That is the bottom line of the discussion, right? And this particular part this is called as the external fragmentation. That is, memory is fragmented, but it is external to the process. Why it is called the external fragmentation? Memory is fragmented, but it is external to that particular process. Getting my point or not? Then what is the internal fragmentation? Internal fragmentation is that the fragmentation is there, but it is internal to that particular process. but it is internal to that particular process. For example, consider take an example here. Say for example P5 process. Okay, P5 process 500K. So this block is allocated to the P5 process. But P5 process requires 498K of memory. So here instead of 500K, so instead of 500K, it requires 498K of memory is required for the complete execution of the P5 process. Right. So what operating system does here, and you have whole of size, and this whole of size, how much size of whole is available? Say for example here 500K of whole, 500K of whole is available. For example, here is 600K, but for simplicity consider the whole of size 500K is available, and the process requires how much memory? It requires only 498 memory. So what operating system does here? What operating system does here? This only difference is 200, 2 KB. So this 2 KB is also allocated, means 500 total memory is allocated to that particular process P5, because it will leave 2 KB of whole, and to keep the record of this 2 KB is very tedious job for the operating system. So total memory is allocated to that particular process. Total memory is allocated to that process. And so though you are allocating, though operating system is allocating the 500K, but only 498K is used, 2 KB is remaining as it is, and that is called as the internal fragmentation of the memory. Fragmentation is there, memory is unutilized, but which is internal to that particular process. Getting my point or not? Which is internal to that particular process, right? So see here, consider the whole of size 18,464, means some figure are taken here. So the memory whole is of size 18,464 byte is available, and the process request is only 18,462. So meaning is that 2 KB or 2 bytes are remains as it is. So what operating system does here? Operating system never returns this 2 KB as a whole, but it is given to that particular process, and it is said that yes, now can use what you want to use it, you use it, or you remains you keep it as it is, right? So process will not use, process only use that much amount of memory, and this 2 bytes will be remains as a internal fragmentation to that particular memory, internal fragmentation to that particular process. So these are the concept of internal fragmentation and the external fragmentation. So the difference between the two numbers is the internal fragmentation, that is this one, 18,462 and 18,464, that is 2, that is called the internal fragmentation to that particular process, right? So memory that is internal to the partition, but it is not being used by that particular process, it is called as the internal fragmentation. One solution for the problem of external fragmentation is the compaction. So we are going to compact, we are going to merge the holes together, and we are going to shift the processes to one side and holes to one side, that is called the compaction. But practically, theoretically though it is possible, but practically it is not possible. And the solution to the external fragmentation is given by the paging. So in the next lecture we have to discuss the paging concept. So I think the concepts are clear to you. Internal fragmentation, what is the meaning of internal fragmentation, what is the meaning of external fragmentation in multiple partition allocation? Just a quick review. Okay, multiple partition allocation. So if we see this multiple partition allocation, so holes are created, we are going to allocate the memory as per their requirement. So what is the disadvantages? As per the requirements, if we are going to allocate the memory to the different processes, they are going to create the small holes inside the memory, and these small holes, they are called, it is called as the fragmentation, and as it is external to that particular process, it is called as external fragmentation. So though in total this memory space is very large, but due to they are not in a contiguous format, that cannot be utilized by the processes, right? And internal fragmentation is that suppose 500K is the memory block and the process requires only 498K. So what operating system does here? Why unnecessarily create the memory block of 2 bytes only? So allocate all the entire memory to that 498K requirement, and the process will only use 498 KB of memory, and 2 KB of memory inside the process remains as it is, and that is called as the internal fragmentation, right? The solution to the external fragmentation, it is achieved with the help of our paging. That paging we are going to see in the next lecture, right? So what we have discussed, we have learned in this session, that is nothing but the single partition allocation, multiple partition allocation, the first fit as well as the best fit and the worst fit algorithm, the external and the internal fragmentation of the memory, the course outcome attainment are nothing but the various memory management technique we are discussing. The questions on this particular topic: how multiple partition is implemented in the system. Explain with suitable example. So you have to draw the figure and you have to explain the multiple partition allocation with the help of the figure and with the help of 5 processes and with their different memory demands. Then explain the first fit, best fit, and the worst fit algorithm that we have to discuss. That already we have discussed, and write a note on external as well as the internal memory fragmentation. So these are the reference book. Always you have to refer the reference book only. So thank you. So we'll stop today for this lecture.